In this video, we're going to talk about the polynomial functions of higher degree. Just to clarify some vocabulary, the first thing that I want to introduce to you is the polynomial. These are going to be written in the form of a sub n times x to the n plus, and it goes on down in descending order until you get to a sub 1 x to the first power plus a constant a sub 0. When we write these in standard form, our terms need to be in descending order based on their degree. Also, the coefficient, which is going to be our number in front of our variable, and we're also going to talk about the leading term, which is the coefficient of the term with the highest degree. So in this example right here, definition of a polynomial, our leading term would be a sub n because it's the coefficient of the leading term. Okay? All right, the first thing we're going to talk about is end behavior. When you're looking at end behavior of polynomials, you have to look at two separate things. The first thing you're going to look at is the leading term, and you're going to determine whether it's positive or negative. Then you're going to look at the degree of the highest of the entire polynomial. Okay, so if the highest degree is even or odd, is going to affect the way the graph looks. Okay. So if your highest degree is odd, for example, this here is our cubic function, so y equals x cubed. Notice that our end behaviors are in opposite directions for the positive and the negative end behavior. And the end behavior as it approaches infinity is going towards infinity. Okay? Whereas when our leading term is negative, our leading coefficient is negative, our end behavior as it approaches infinity is going to be negative infinity going down. Again, because our degree is odd, the end behaviors are going to be opposite of each other. Okay? This is opposed to when our end behavior, our degree is even. If our degree is even and our leading term is positive, the end behaviors are both going to be going towards infinity. If our degree is even and our leading term is negative, both of our end behaviors go towards negative infinity, like in this example here. Okay? All right, the next thing that we need to talk about is the zeros of a polynomial. There's a good example on page 198 showing you how to find the zeros of a polynomial, either algebraically, where you factor and then use the zero product property, or graphically, where you basically look at the graph and see where it touches or crosses the x-axis. Okay? What we are going to talk about next is called multiplicity. This is going to help us talk about the zeros of a polynomial. Okay, there's a definition in your book, and it kind of gives it a little bit more detail, but basically the multiplicity of a zero of a polynomial, if x minus c all to the m power is a factor, then c is a zero with the multiplicity of m. So for example, let's say that you had f of x equals x plus 2 cubed times x plus 1. Okay? We have two different zeros here. The first one is going to be x plus 2 to the third. This is going to give us a zero of x equals negative 2. And then x plus 1, which is going to give us a zero of x equals negative 1. Now, x equals negative 2 is a zero, but because it occurs 3 times, it has a multiplicity of 3. X minus 1 is a zero. It's to the first power here, so it has a multiplicity of 1. We typically don't write it with multiplicity of 1. I'm just writing it here to show you what it means. Okay? All right, let's talk about what the multiplicity does to the graph. Okay? If our multiplicity is an odd number, so if our multiplicity is 1, 3, 5, and so on, the graph is going to cross at the 0. So whatever the 0 is at, that's where the graph is going to cross it. If it's an even multiplicity, the graph is going to touch at touch the x-axis at that point, but it never will cross it. Okay? I'm going to show you three examples here below. Okay? In the first one, we have y equals x minus 1 squared. Okay? Our multiplicity is 2. that means our graph is going to come down and touch it at the point, and then it's going to continue back up. So it's never actually crossing this x-axis here. When our multiplicity is 3, what's going to happen is our graph's going to come up and flatten out a little bit and then continue on up and crossing it. Okay? And in the last example, there's 2 zeros in this case, and they're both with multiplicity of 1, meaning they're both going to cross the x-axis. So here's one of our roots, and here's the other. Notice these ones just go straight down and cross it in both sides, opposed to the triple root here, the multiplicity of 3, where it comes up, flattens out, and then continues on. All right, let's look at an example of putting all of this together. Okay, so without our calculators, we're going to sketch the graph of f of x equals x minus 1 cubed times x plus 5 squared. Okay, the first thing that you're going to look at is determining what the degree of this function is. Okay, in this case, if we were to, multiply x minus 1 times x minus 1 times x minus 1 times x plus 5 times x plus 5, our leading term, our leading degree is going to be 5. So the degree in this case is 5. Okay, and since it's already factored for us, this is nice because we can find our zeros quickly. We have zeros at x equals 1, and this is going to be a multiplicity of 3 because it's cubed, and because 3 is an odd number, we know that this is going to cross the x-axis at that point. Okay, our second root, x plus 5, we're going to set that equal to 0, so x equals negative 5. Our multiplicity here is 2. And this one, because 2 is an even number, that means it is going to touch the graph but never cross it. Okay. All right, let's talk about the end behavior for a second. Because our degree is 5, which is an odd number, that means our end behaviors are going to be opposite of each other. So the first one we need to find is the limit as x approaches infinity of our function. Okay? So we're going to look at our leading coefficient. Now we know if we multiply this all out, our leading coefficient is going to be x to the 5th. So the coefficient of x to the 5th is 1, which is a positive number, meaning that as we approach infinity, we are going to go towards infinity. Okay? So that means that the opposite, when we do the limit as x approaches negative infinity of our function f of x, is going to equal negative infinity. Okay? So this is important when we graph it. So we have our two roots, one at x equals 1 and the other one at x equals negative 5. So we can go ahead and plot both of those. Okay, so now what's going to happen is if we go from left to right, see here where x equals negative 5. Our multiplicity is 2, meaning it's going to come up and touch it kind of like a parabola does. Okay, we also know that as x approaches negative infinity, our function is approaching negative infinity. So we're going to start down here. We're going to come up and we're going to touch 5, but we're not actually going to cross over. Okay. Now let's talk about what happens over here at x equals 1. We have a multiplicity of 3. That means it's going to come up, flatten out a little bit at 3, and then continue on. So our graph is going to look something like this. See how it flattens out a little bit right there. Okay. So again, this is just a sketch of our graph. It's not going to be 100% accurate based on our y-intercepts and whatnot, which we could find. But this is in general what it's going to look like for us. What's important is finding our roots and what it looks like at those roots. Okay.